All right, good day, everyone. Welcome to day 4 of Introduction to Hydrogen Fuels. I'm Dr. Rita, and I'll be taking you through the last day of this course. So today, we're going to be looking at the hydrogen safety risk, just touch a bit about the emissions and cost of hydrogen. Okay? And this is all we have covered so far up until today. So before I start, I will give participants opportunity to ask any question from anything that was covered yesterday or day 1 to 3. And while the questions are coming in, I would just like to say for day 3, what we covered were the different ways in which we can, change the density of hydrogen so that it's easy for storage and transportation. One of them is compression, and the other one is liquefaction. Compression involves increasing the pressure. Liquefaction involves reducing the temperature. We looked at different storage technologies, physical, material, and subsurface. And then we looked at different methods of storing hydrogen from transportation to different forms in which it can be converted at destination. One thing that I think I skipped, even though it's on the slide, is blending. And so what blending means is basically if you have a pipeline that is, let's say, carrying methane, you can combine your hydrogen and methane in the same pipeline, mix them together, as long as you're able to use them together at your destination, or if you think you can separate them. But mostly it's putting a quantity of hydrogen with your methane, and then you can transport them together. So for us to look at the safety implications and risk associated with using hydrogen as a fuel, we need to go back to some of its properties. So what you see here on the slides, first of all, hydrogen is non-toxic, okay? It dissipates rapidly when it's released. What it means is that if hydrogen is going to leak from a container, it's going to diffuse very quickly and dissipate into the environment, okay? So very rapidly. And it has a high auto-ignition temperature. Now, for us to have combustion or ignition, we need 3 things. We need the fuel, we need oxygen, and then we need a spark or fire or something, we need a spark, something to ignite that fire. Now, in some cases, we can heat up a system in the absence of that spark, and we'll still be able to cause ignition. Now, hydrogen has a very high auto-ignition temperature. So that's that temperature at which you need to raise the system to, that in the absence of that spark, hydrogen will ignite. It means you need to really increase the temperature of your system for it to ignite by itself. So because it's very high, this is a positive for hydrogen. So these 3 things that are listed here, that is non-toxic, it dissipates rapidly, and it has high auto-ignition temperature, they are positives for hydrogen in terms of safety. Now we're going to look at the things that make it a big risk and are safety issues. First of all, hydrogen has a wide range of flammable concentration limits, and I'm going to explain that subsequently. It has a low ignition energy, lower than gasoline or natural gas. I'll also explain that. It burns with a nearly invisible flame. So imagine that there's fire somewhere and you can't see it. And then 4th, hydrogen makes metals brittle, most metals, so these have their additional implication for storage facilities, transportation facilities, and so on and so forth, okay? So there's a question in the chat box. This should be for Ahmed. It just says, after taking the quiz, do we have to just click the mark as done option, or we have to upload any type of file? I wouldn't have the answer. Ahmed will be able to address that, okay? So let's look at the flammable concentration limit, okay? So it's that concentration of a given gas for which, in the presence of oxygen and the presence of the spark, is going to ignite, is going to cause a fire. And if you look at this diagram here, this sloping triangle here, on this side, we don't have enough hydrogen for us to cause combustion or ignition. And on this side, the ratio of hydrogen to oxygen is so high that we would not be able to have ignition. So we need a certain amount of hydrogen to be able to mix with oxygen for us to have the flames or the ignition. And for hydrogen, it's very wide. It's from 4% to 75%, which means as low as having 4% hydrogen in your air combined with oxygen in the presence of a spark, you are going to have ignition, combustion. And this will continue up until the percentage of hydrogen is 75 in your air mixture. So this is not something very good, okay? What it then means is that if you need to stop a fire due to hydrogen, you have to try to reduce the concentration, because as the concentration is increasing, it's going to still keep burning, okay? Also on this figure, we have what we call explosion limits. The explosion limits are inside the flammable limits. So we need higher concentration to have the lower explosion limit than we would want for we would use for flames, to generate flames, okay? So the flammable concentration limit 4 to 75, the explosion limits are within that bracket. The figure on the right compares these flammable limits to other fluids, gases that we know. And we can see that hydrogen is quite wide. If we compare it to diesel, even though diesel will ignite at very low concentrations, once it's much more than 5.5%, we would no longer have an ignition or flames taking in our system. So this is how it compares to different fluids. The other thing we'll talk about is the ignition for hydrogen. So I talked about the auto ignition temperature, and it's just the minimum temperature to initiate combustion in the absence of ignition. Now for hydrogen, the value is quite high. I mentioned about 5, it's about 5 something in degrees C, 500 and something. In Fahrenheit is 932. So yes, on the slide, so it's there, 5H5, it's very high. Now, the ignition energy is different. It's not a temperature, it's not energy. It's the amount of energy that has to be applied into that our fire triangle. We have the oxygen, we have the fuel, and then we need a spark. That energy that needs to be applied for us to have combustion. The ignition energy for hydrogen is 0.02 millijoules, very small, okay? So what does it mean? It means that if there's a spark somewhere, even if it's an invisible spark, we cannot see, but there was a spark, and hydrogen is present and oxygen is present in, the right proportions, then we would have a fire. It also means that, there's sometimes when we have static electricity in our bodies, maybe based on some clothes that are very dry or something. That kind of electricity can cause ignition in the presence of hydrogen and air and oxygen, okay? So that's not a good thing for hydrogen. So we need to be very careful with hydrogen because of the ignition energy required is very low. Now, the flames from hydrogen. The flames from hydrogen are difficult to detect, especially in daylight, because it produces something that is close to invisible. So this figure on the left is somebody trying to feel for hydrogen, like that there's a fire, because they can't see it, okay? Hydrogen, we can't see the flames. It does not, it's non-toxic. It does not produce smoke, so we don't see it unless you now bring in something else that will combust. And it has low radiant heat, so it may not burn as much as some other gases, okay? And what it means is that people can easily, there can be a hydrogen fire somewhere and people can actually walk into it because they are not seeing it and they are not really feeling it, okay? So on the right, we just show in broad daylight, this is flame from propane and this is flame from hydrogen, which you can almost not see, okay? Still on how hydrogen burns, okay? Hydrogen is considered, the fire from hydrogen is considered safer than that of gasoline for several reasons. First of all, the hydrogen, when it burns very quickly. It has a very high speed of burning. It burns, as you can see, vertically upward, as opposed to gasoline that is spread all around, okay? But it burns quickly. So once it exposes in a couple of minutes, hydrogen is done burning. While something like gasoline will spread and will keep burning and can heat up so many things. Also, it's kind of localized. You can see that the flame from the hydrogen is kind of localized to where the source is. But with gasoline, it's going to spread. So this is why the flames from the fire from hydrogen, they are safer. However, they are difficult to extinguish. So you can't use the normal procedures you use for quenching or extinguishing a fire because it's happening so fast. You don't even know where it's going to. And so usually they just recommend that you stop it from the source and you just wait for it to burn out. It will burn out by itself in a couple of minutes, okay? So if you now get an external material, that external material, if it now gets caught, like it burns with, in the presence of the hydrogen, that's when you begin to see the smoke and the soot. For hydrogen by itself, you wouldn't see the smoke and soot. So the figure you see here is trying to say that because we don't easily see hydrogen flames with our naked eyes, we need things like thermal imaging to be able to identify the hydrogen. So with this thermal imaging tool or this detector, we would be able to see the flames, which we would not be able to see with our naked eyes. This other one is using something they call corn broom, which used to be one of the ways of identifying that there was a hydrogen fire. So this corn broom will now catch fire, and then you will know that, okay, you have something going on here. Any questions on hydrogen, fire, ignition, etc.? Okay. Let's look at material compatibility. Now, remember that hydrogen is a reactive substance, and its reactivity poses a lot of issues with the kind of materials we're going to store it in and use it for transportation. So there's the property of hydrogen. It's highly diffusive. So it can easily move, even within gases, it can move into solids, it can move through liquids. It's diffusing. Okay, so that's one of the properties that we need to bear in mind with material compatibility. Okay. Okay, so there's a question, what temperature can hydrogen reach when burned? I don't have that number off the top of my head, but it's usually lower than we would expect for other gases. In terms of the radiant heat, is lower. I could find that out. I can confirm it and get back to you. Okay. So when we are lower than 150 degrees C. That's when we see these issues with material compatibility. But above 150 degrees C, the issue of material compatibility is not a problem. Okay. The second thing is that if we have something like very high strength steel, these ones are more susceptible to compatibility issues with hydrogen. And so if you want to choose a material that you would use for storing or transporting hydrogen, you don't want very high strength steel. So what would happen when hydrogen comes in contact with the metal? It will diffuse into that solid. When it diffuses, it goes into the lattices, the edges of the molecules that make up that solid. And when it goes into all those edges, which is what we see there, they now come together and form. And when they come together, they weaken the material itself. And once they have weakened this material, it then means that anything we are doing with that material, it's now more susceptible to damage. So it would make a material that was previously ductile, that is, you could easily bend it without breaking it. It will now make it easy to break. And so that's what happens when there's hydrogen embrittlement. You begin to see cracks, you begin to see breakage and damage to your structures. So the ways of trying to work around it is through what we call material selection. There are certain materials that are not very high strength, and also they do not, the concentration of, the different materials used to make them do not allow them to be very susceptible to embrittlement by hydrogen. So these are some of them that I've listed here. I have the austenitic stainless steel, aluminum alloys, low alloy ferritic steels, the CMN ferritic steels, and copper alloys. But there are some materials that, even though they might be very good for other gases, we need to avoid for hydrogen. So high strength steels with so much iron in them need to be avoided. We have these gray malleable and ductile cast irons, nickel alloys, and titanium alloys. So these are the ones we would want to avoid for hydrogen. So there's a question on if the low radiant energy is something that is in favor of hydrogen safety. Yes, it is something that is in favor of hydrogen, as long as we don't have large volumes of this hydrogen that is being burnt and being exposed, because it's quite diffusive, right? So if you have a lot of volume, even that radiant heat can have impact. But yes, it's a more positive thing that we have low radiant energy for hydrogen. Okay, so how do we make hydrogen safe in our operations? One of them is to use technologies for leak detection. So we have to, first of all, try to find ways of identifying the leaks. Where is it coming from? Before it goes into combustion. But if it does, then we need to apply things like thermal imaging to try to track where it is and what the size is. The second one has to do with the kind of engineering designs we do, what kind of ventilation systems. So for instance, we need a certain ratio of hydrogen and oxygen for us to have combustion in the presence of a spark. So if we have a very highly ventilated room, it means that the oxygen concentration is very high. Then the hydrogen concentration will be low. So even if we have a leak, we may not necessarily have a fire in the presence of a spark, because the concentration of hydrogen is so small compared to the overall concentration of the place where you are. So like in some cases, like at the lab, you will quantify what is the size of my room. And assuming this room is filled with air and I know the percentage of oxygen that I have, I need to know what is the maximum size of hydrogen cylinder that I can put inside that room, so that if all of that hydrogen leaks out and it comes in contact with the air and the oxygen, it's not going to leak. It's not going to, not that it won't leak, but it won't cause a flame or combustion. The other thing we look at is in the materials. As we have seen, there are certain materials that are better for hydrogen and others. And so you do careful material selection, even to the seals that you're going to use for your system. You need to do proper material selection to prevent hydrogen embrittlement. And if there's any incident that occurs, you might have a small spark and a small fire somewhere. And if the material that is there is one that, melts very easily at even low temperatures, then it's also not good for you. So we need to think about all the materials that we're going to use in the whole value chain. And then, of course, you can put everything together, all the equipment, all the processes, but the people need to be aware. They need to be aware of the risk associated with hydrogen, what it can do, how to prevent it, and all of that. Because when a hydrogen incident occurs, it's usually a big one when it does occur. Okay? All right. Any questions? Okay. For those that have participated in all the quizzes after the online lecture, do we still need to attempt it in the Google Classroom? I think that would be a good idea. Just do it so that you can have it recorded. The questions wouldn't take you more than 10 minutes to do, or even 5 minutes. So please do that. Okay. So moving away from the safety of hydrogen in itself, we're coming back to look at the carbon intensity of hydrogen. And I just put this slide here so that you can visualize, that carbon intensity associated with different ways in which we produce hydrogen. Okay. A couple of things, disclaimers that I would say. So there's a question. Did you mention something about products that can detect a hydrogen flame during combustion? Yes. There are some flame detectors and thermal imaging detectors that enable us to see the hydrogen flame when it's undergoing combustion, because we can't see it with the naked eye. One of the things I would say, though, is that in the night, if it's very dark, you can see a hydrogen flame. But in the daytime, it will be very difficult just because of the bright light. Okay. So here, I'm going to put some sort of disclaimer looking at this figure. So first of all, we have white hydrogen here. So white hydrogen is the one we would say comes from natural hydrogen, okay, or a byproduct of an industrial process. So I wouldn't put this type of solar here, but solar will fall under the renewables or green hydrogen. Okay, so use this with some sort of pinch of salt, how to say, okay? The other thing is you can see how the carbon intensity ranges for different methods of producing hydrogen. So remember, the carbon intensity is the amount of CO2 that is generated when we are trying to produce hydrogen from a given method. Okay, so this one has a very wide range, which is the black hydrogen, the one from coal. We also have gray hydrogen having some range, blue hydrogen, and it's going to depend on, so for instance, this blue hydrogen, which is natural gas plus CCUS, will depend on how much CO2 are we able to remove from the process and store in the whole system. Okay. So it ranges, okay? Even from renewables, it also ranges as well. But we can see that we're going from high basically to low, okay? I'm not quite sure what this one, oil sands, is. I have not seen that one before, and I'm not sure why the carbon intensity is that low from oil, okay? But yeah, so this figure is just for you to have a visual idea of what the different carbon intensities of the different methods of getting hydrogen are, and you can always associate them to their color of hydrogen. So we'll go over to another topic, okay? So we've looked at the safety and environmental implications of hydrogen. We're going to talk about what we call the levelized cost of hydrogen. Okay. Okay. There's a question. What is the unit of the carbon intensity of hydrogen? The unit is kilogram of CO2 equivalent divided by the kilogram of hydrogen. So for each kilogram of hydrogen you have, what is the CO2 equivalent that you generate? So if you have other greenhouse gases, maybe methane, you have NOxes, you will convert them to an equivalent kilogram of CO2 to be able to measure this CO2 intensity. Okay. So there was a question that where is the CO2 from green hydrogen? So most of the times when we do green hydrogen, if you do what we call a life cycle assessment, you're going to look from the time when you started producing your solar panels or your wind turbine to the time you finally have it ready to generate the hydrogen. You will find out that perhaps to be able to build the blades of your wind turbine, it was a natural gas plant that generated electricity. The source was not entirely new, clean, or renewable. So when you take that into consideration, you have some percentage of CO2 that is related to that value chain before you eventually generated your hydrogen. Okay, so we get these numbers from life cycle assessment. You start from the beginning, from when we started even producing the solar panels, the concentrated solar plants, the wind turbine, up until the time we started generating the hydrogen. Okay, so that's where we see some CO2 coming in. Okay, what other question? How do we relate the CO2 to a method? So is it that the higher the CO2 intensity, the better? So the answer will be no. If your CO2 intensity is high, it means that when you're generating 1 kilogram of hydrogen, you are generating a lot of CO2. And you really don't want to generate a lot of CO2 because that CO2 is what is going to go into the environment and cause and make us start a decarbonization process. So the lower the CO2 intensity, the better the method of sourcing for that hydrogen or producing the hydrogen. All right. Yes, the lower, the better. Okay. So let's look at cost of hydrogen. So there are different metrics out there for looking at cost of energy systems. There is one of them called the levelized cost of energy, LCOE. I am not discussing it today. We'll focus on hydrogen. But just for you to know, it's basically looking at how much did I spend on this energy system compared to how much energy it is supplying. So for instance, if I have a geothermal power plant, I have a solar power plant, and I have a natural gas power plant, okay? I have those three. and I want all of them to generate 10 megawatts of electricity, okay? Now, the one that gives me the highest cost to generate that 10 megawatts of electricity is not good for me because it's making me spend more to generate the amount of energy that I want. Sometimes hydrogen can be put into that category if we're looking at hydrogen as supplying electricity. But that's not what we're going to focus on today. But I just want you to know there's something called LCOE, levelized cost of electricity. We use the same principle to get the levelized cost of hydrogen. The levelized cost of hydrogen is now saying that with all the methods that I have to produce hydrogen, if I want to produce, let's say, 1 kilogram of hydrogen, for instance, 1 kilogram, how much am I going to spend to produce that 1 kilogram of hydrogen? Okay. And we basically want a lower cost to provide that 1 kilogram of hydrogen. So how do we calculate this levelized cost of hydrogen? Okay. We are going to take the net present value. So we think about the lifetime for which we're going to be producing this hydrogen. Let's say it's 20 years, okay? So in these 20 years, I'm going to get an electrolyzer. I'm going to maintain my electrolyzer stacks. Maybe I'm going to change them frequently. Maybe I need to buy water. So those are my operating costs, while the cost of the electrolyzer itself is my capital cost. And then I'm going to see how it's going to behave over that 20 years. Maybe I might have depreciation for my electrolyzer, and then my operating costs that will be coming every year. So I'm going to take all that cost together, and I'm going to discount it to my present day. So that's what we call the net present value of those costs, okay? So I basically want to see the cost of my whole system over the life of my project for today. So that goes into your numerator. Then I'm going to look at this for the same 20 years. How much hydrogen am I going to be producing? Okay, so I'm going to perhaps maybe in the beginning, my electrolyzer is very efficient, and so I'm producing very high quantities. But as I keep using it, the efficiency is reducing and my hydrogen quantities are reducing. I'm also going to discount it using the amount in kilograms of hydrogen. I'm going to discount it over the number of years to present day. And so what I will have at the end of the day is a cost, dollar on top, and quantity, a discounted quantity in mass, kilograms. So the unit of the levelized cost of hydrogen is dollar per kilograms. Okay? So now the figure we see on the right is looking at the levelized cost of hydrogen in different locations and for different kinds of systems. So alkaline electrolyzer, the PEM, the SMR with and without CCS, okay? So we can see the range, but one of the things that stand out, okay? One of the things that stand out is the electrolyzer costs are much higher than the SMR cost, if you look at it. So that's one of the things to note, that currently the cost of producing hydrogen through electrolysis to make our hydrogen green is more expensive than steam methane reforming, okay? You can see that for steam methane reforming is somewhere like 1, while for when you bring in CCS, it becomes much more, but still it's cheaper than when you're using electrolyzer. So there's a question on producing hydrogen directly from seawater. So most of the commercial electrolyzers do not use very saline water. And so there are different technology that is being developed to use high salinity water for generating hydrogen, okay? There's another question. Where do new technologies like electrolysis in supercritical phase lie? by comparison to PEM. I am not sure I have the numbers now, the figures, but I'm sure that if it's still in the research and development phase, we may see the potential for it to reduce costs, improve efficiencies, but we need to see how it will behave when it is scaled up, when it's commercial. So the HTEs, the high temperature electrolyzers, they are still being, developed. Like we haven't gotten them to the commercial stage yet. Okay, so this figure is looking at it by different locations. There is another one that looks at it. This one was done specifically for California, okay? And in this particular study, they brought in the incentives. So there are some incentives that are put, policies. So for instance, if you are going to be doing something like CCS, you're going to be capturing, you have some tax credits, okay? You have some low carbon fuel standards that are taken into consideration. So if you're trying to generate low carbon fuel, you get some, credits for your cost, okay? So what happens if we look at the left, this is steam methane reforming to generate hydrogen with some incentives. And all of this are different components, like if it's just plain steam methane reforming, if we have some blending of the gas that we're using, if we, this one is with CCS, and the values that we have here are like averages that people see. So if we go to the previous slide, okay, let's take, for instance, which one do we have? If we take, for instance, SMR with CCS, you will see that that one is more expensive than just plain SMR without CCS, okay? However, when you begin to put in incentives, like for how much CO2 you've captured, there's an incentive. If you're using a low carbon fuel standard, there's an incentive, etc. It tends to bring the cost low. So incentives really help to reduce the cost, to bring down the cost of these technologies that are trying to reduce carbon from our systems. On the right, we see electrolysis. Now, electrolysis directly with energy from the grid, where we take energy from the grid, power our electrolyzer, is very expensive. However, if we use things like solar directly, or we combine solar and wind, we are able to reduce the cost. Then this is solar with battery, so which means that you have a storage system. And so that storage system is battery, okay? And so this kind of increases the cost because of the storage cost, the battery storage cost, okay? So in general, steam methane reforming has a lower cost than electrolysis. We saw it in the previous slide. And then with incentives, we're even able to bring down the cost of some methods. So if we really want to, advance the low carbon system economy, we need to really think about incentives and hope that these incentives last enough for us to scale up to be able to produce low carbon fuels. So any questions on the cost of hydrogen? All right, so there are two things that I will talk about before we close for today, okay? One of them is okay, there's a question. It says, why is direct from grid more expensive if solar energy is more expensive than normal grids? So it's because when you're using solar energy directly, you are just paying for the what is your cost is basically the cost component associated with that, let's say solar panel or CSP or whatever source it is, that let me say solar panel that is directly connected to your electrolyzer. With the grid, you're paying the cost of the grid, like how you pay for your electricity bill. And that one overall will be higher than just a solar plant dedicated to your electrolyzer, because you're able to just direct all the energy from that solar plant to your electrolyzer. So something I want us to touch on before we close is where hydrogen fits in terms of energy storage systems. So there are different energy storage systems. I didn't go into the details in this particular course. In other courses I teach with more time, I go into all of them. But we have what we call the capacity, which is the volume of energy that can be stored. Okay. It's a unit of energy. Okay. So megawatt will be power, megawatt hour is energy. And then the discharge time means if I now collect this energy that I stored, how long can this energy last me? Okay. So with hydrogen, we can see that it's on the high storage capacity. We can store large amounts of energy in hydrogen. And then when we eventually want to use this hydrogen, it can last us from a couple of hours, even 2 months. So it's something that is quite positive for hydrogen as a storage mechanism. Okay. And then the last thing that I'll talk about is the global hydrogen trends. Now, if you see this figure, okay, what we have here is how the use or the demand for hydrogen has been evolving with different things. So the blue here, for instance, is refining. The brownish here is industry. And that has been the predominant industries that have demanded hydrogen. But as we begin to move forward, there's going to be the application of hydrogen for power, syngas, transportation. Ammonia should be somewhere there. Okay. So what it means is that the demand for hydrogen is going to increase drastically. Storage requirements are also going to increase. Okay. And so there's going to be demand for hydrogen in the future for these different sectors. You can see what we have for something like transportation. So for fuel cells based off hydrogen will be there. And so you just know that the hydrogen economy is possible, but we need to overcome some of the hurdles we have in terms of materials, in terms of storage and transportation to enable it. So I will first of all say thank you all for listening to me through the last couple of days. And we will still have one more quiz. Do you have any questions so far before you start the quiz? The quiz you're going to do with me now is your Kahoot quiz that you normally do, your 10 questions. But afterwards, to get your certificate, you will do a separate quiz. And that one, it's a summary of all we did from day 1 to day 4. I know you all will do very well. You do that one and you get your certificate. Okay? All right. Any questions for me? All right. Let's go ahead. And if you need to reach out to me afterwards, if you have any questions, please find me on LinkedIn, make a connection, and we can continue the conversation there. Okay? Thank you. I'm going to stop share for our final quiz. Thank you all for your comments, your thanks. I'm seeing them here. So the PIN is here. So join in, it's 8743906. So Ahmed, there's a question I'm being asked if the quiz is uploaded on Google Classroom. I believe that is the case. All the quizzes should be uploaded on Google Classrooms. The benefit you have for having done some of them through the Kahoot is you have an idea of the questions and you can go and prepare before you answer those quizzes on Google Classroom.
So for quizzes on Classroom, we post them right after we post the video.
Okay.
So I believe quiz number 1 already is there. Quiz number 2 will be posted today.
Okay. All right. But the other thing is, if you want, I could always send you those that participated in the Kahoot in case they don't do the Google Classroom quiz, just for you to know that they actually participated. It's just that sometimes Kahoot doesn't let us get full names, so. Okay, are we all ready? I'll give 1 more minute for us to join and then we go. So Ali Abubakar, I saw your question. Connect with me. Let's discuss, okay? All right, we start. So I'm going to stop share, okay? Questions are true or false. High autoignition temperature is a positive property of hydrogen. High autoignition temperature is a positive property of hydrogen. Okay. Hydrogen has a lower ignition energy than gasoline or natural gas. Hydrogen has a lower ignition energy than gasoline or natural gas. Hydrogen has a wide range of flammable concentration limits in air. Hydrogen has a wide range of flammable concentration limits in air. Hydrogen's explosion concentration limit ranges from 4% to 75%. Hydrogen's explosion concentration limit ranges from 4% to 75%. That was a trick question. Okay, an invisible spark may have enough energy to cause ignition of hydrogen. An invisible spark may have enough energy to cause ignition of hydrogen. Good job, all of you. Hydrogen embrittlement occurs at temperatures above 150 C. Hydrogen embrittlement occurs at temperatures above 150 degrees C. The LCOH for electrolysis is smaller than the LCOH for SMR. That is, the levelized cost of hydrogen for electrolysis is smaller than the levelized cost of hydrogen for SMR. Projections indicate that hydrogen demand will continue to rise. Projections indicate that hydrogen demand will continue to rise. Hydrogen fires are safer than gasoline fires. Hydrogen fires are safer than gasoline fires. Last question. I have learned a lot about hydrogen as a fuel. I have learned a lot about hydrogen as a fuel. All righty. And so that one has only one answer. All right, so just to say congratulations to all of you that have participated in this last 4 days, okay? And congratulations to Ali, Abubakar, Donald, and Tony, okay? Frank and Loic, well done as well, okay? All right, is there any questions for me? No, not yet. All right. So in that case, there is nothing else from my end. Thank you all very much. Please remember to do your final quiz and to get your certificate after all the videos have been posted. Okay, take care.